Hello, welcome to the first talk in this session. It's going to be Joe Jevnik, title available on request, Introduction to Lazy Evaluation. Have fun.
Hi, everyone. Thank you for attending. Today, we're going to talk about lazy evaluation. Before we talk about lazy evaluation, I'd like to revisit how we execute programs normally, and more specifically, how we execute Python programs. So if we have some arbitrary function, here we're going to call it f, takes two arguments, a and b. This function is going to print the string calling f with a equals and then the value of a, and b equals the value of b. Then this function is going to return the sum of a and b. When we write the line of code a equals f of 1 and 2, what the Python interpreter does is it looks at this line and it says, I need to evaluate the arguments to this function call. So it's going to evaluate the literal 1, which produces the value 1, evaluate the literal 2, which produces the value 2, and then it will immediately enter this function and begin executing lines in the order that they appear in source code. So we're going to hit the first line, which is print and our format string, and what that will do is format the string to produce the actual string we want to print. So we're going to generate calling f with a equals 1 and b equals 2, and then we're going to feed that string to the print function, which will print it to the terminal. Then we're going to hit the line return a plus b, which is going to add a and b together and return that to the caller. So when we write this line, we see that we've immediately printed. So we know that we've already called our function. And when we look at the value of a, we have the integer 3. So we have a concrete value. We can then use this value a in another expression. For example, b equals f of a and 4. We're going to do the same thing when we execute this code, where we load a, which will fetch the value, which is 3. We're then going to load 4, and we're going to enter our function again, generating the format string, calling f with a equals 3 and b equals 4, printing that to the terminal, then adding these numbers and returning it. And when we look at b, we see that it's 7. So we've, again, immediately produced a concrete value, which is the result of this expression. What we're describing here is an evaluation model, which is the way that we execute programs. And in particular, we're describing what's called eager evaluation. Eager evaluation is where you evaluate expressions as they appear in source code. So you go line by line and just start executing code. Expressions immediately produce a concrete value. So when we had the line a equals f of 1 comma 2, we immediately produced the value 3. And eager evaluation is a choice. So a lot of people, when they learn programming, they learn that computers go line by line and they execute code. But that's not the only way that you could choose to execute code. This is just a choice that has been made for you by the programming language we chose. I will say, though, that eager evaluation is a very good choice. The reason it's a good choice is that it's very easy to reason about the behavior of your program. Just by looking at the code, you can get a sense of where it's actually going to do work, which lines are going to be expensive, and so on. We can reason about the performance of our program because we know that when I write a line of code that calls a function, that's where that function will be called. And then, again, it's easy to debug our programs because when we write a function call, it immediately produces the value. So all of these reasons led Python to choose eager evaluation as its model because Python strives to be easy to read and understand. There are alternatives to eager evaluation, and the one that we're going to talk about today is lazy evaluation. Lazy evaluation first has a requirement that all of your expressions must be pure. And what I mean by the word pure is that for any given function call, given the same arguments, we will always return the same value. So an example of a function that is not pure is something like random int or get character from standard in. Every time we call this function, we're going to get a different value, and that's okay. The functions that we're going to be talking about today are functions like integer arithmetic, where every time I execute this function, I will always get the same value from the same inputs. In lazy evaluation, expressions are, instead of being evaluated as they appear in code, they're evaluated when we need to know the result of the expression. In order to do that, expressions produce what's called a thunk instead of a value. A thunk is an object which represents some computation to be performed later. The word thunk is just a term of art. It doesn't have an intrinsic meaning. It's just what people use to refer to this deferred computation object. Another name for a thunk is a closure, and this name might be more intuitive as we go through some of the examples. Python provides some tools for defining these deferred computations, and the most important one, and the one we're going to talk about today, are functions and lambdas. The reason we can use a function to defer computation is because when you define a function, you don't immediately execute the body. You only execute the body of a function when, and more importantly, if you call the function. Another tool that Python provides for implementing lazy evaluation are iterators and generators. We're not going to talk about them today because you could fill an entire talk with just this concept. So using only functions, we can write our example from before in a lazy style by wrapping all of our expressions in a lambda. So when we execute this line, what the Python interpreter does is instead of executing the function f to produce the value 3, instead it just produces an object which knows how to produce the value when we request it. But the function has not yet been called. Importantly, you'll notice that we have not yet printed the line calling f with a equals 1, b equals 2, because the function hasn't been entered. If we look at the value of a, we don't have the integer 3, a concrete value. Instead, we have this object which represents the computation required to produce the value of our expression. So we can say that a here is a thunk, and it's a thunk implemented with a lambda. We can still use this deferred expression to generate a larger expression. For example, we can say b equals f of the value of a and 4. When we evaluate this line of code, we still have not yet called f even a single time. Instead, we've just built up a larger computation which will use the value of a. But we haven't printed either calling f with a equals 1, b equals 2, or calling it the second time with whatever the value of a and 4 will be. So if we look at b, this is also a thunk. When we finally want to know what the value of this expression is, we can enter the function, and we will see that we first print calling f with a equals 1, b equals 2, followed by calling f with a equals 3, b equals 4. Because to get the value of b, we first need to get the value of a. One way of thinking about this concept is that what we're defining is instead of a value, we're defining a tree of computations required to produce this value. So we could define a tree that represents the same thing as the lambdas that we wrote before. And what this tree would look like is we start with some leaves, 1 and 2, and these get fed into the function f, which gets stored in the name a. We then create a new node, which is a and 4 getting fed into f to produce b. So when we have a reference to b, that lambda, where we did not yet compute the value, this is really a representation of this tree structure. When we finally want to produce the value and know what the result of our computation is, we start at the deepest leaves of our tree, in this case, 1 and 2. And we're going to actually enter the function that they're getting fed into to know what the result of that function call is. So we would end up with another tree, which looks like a and 4 getting fed into f to produce the value b. But at this point, we now know that a holds the concrete value 3. And we can repeat this process until we have no more function nodes in our tree, and we just have a single value, which in this case would be 7. This tree system works very well for some expressions, but it falls down. For example, if we define a new subexpression, which is lambda of f of ab, and then create a larger expression which uses this subexpression more than once, for example, f of subexpression and subexpression. When we want to evaluate this function and know what the result of this expression is, we will get calling f with a equals 1, b equals 2, and then calling f with a equals 1, b equals 2 again. And that's because to evaluate this expression named value, we need to evaluate subexpression twice to feed that to the f function to get the value. If we looked at this with the tree representation, we would see something that looks like this, where we have f of a and b and f of a and b, and these get fed into f again to produce our result. Because we know that all of our functions are pure, this is not the most efficient representation for this computation. We know that f of a and b is going to return the same value, so that subtree on the left and the subtree on the right are actually the same thing. A more compact or efficient representation of this computation would be a graph, which has a and b getting fed into f, and now this node has 2 outgoing edges, which both feed into f to produce the result. So this graph representation has us only evaluating f of a and b exactly once. If we want to get this graph representation from their Python code, we're going to need a more advanced thunk, or a more advanced way of representing these deferred computations. Right now, we've talked about what are called naive thunks. So these are the things that look like lambda of f and a and b. So these are a great simple way of representing a deferred computation. Unfortunately, these are slow. And the reason that this is slow is that we're not taking advantage of the function purity. So every time I want to get the result of this computation, I need to reevaluate this function to know what the value will be. One thing that we could do to speed up our graphs is we can memoize the results. Memoization is where you remember the result of a computation, or you cache the value computed from a function call. This means that expressions are computed at most one time. And I say at most because, again, if we never need to know the result of an expression, we don't have to evaluate it at all. And a very important prerequisite for any memoization is that our functions are pure, because we would not want to cache the result of a function like get character from standard in, because every time it's going to return something different, even though the arguments haven't changed. So what we want to do is define a more advanced structure to store our computations. So we're going to define an abstract class called thunk, and the interface for this class is just a simple function call. We're also going to define a function which evaluates our expressions. And what this function does is it says, while the expression is still a deferred computation, evaluate the expression, and continue doing this until we no longer have a deferred computation, meaning we've collapsed the entire tree into a single value, and then we can return that value. The first kind of more advanced thunk that I'd like to talk about is a cell thunk. So we start the definition of our cell thunk with a sentinel object called not evaluated. This is a value which can never be the result of an expression in our system. The signature for our cell thunk takes the code that we want to execute to produce the value, the arguments that we need to feed to this function to produce the value, and then we're storing on self at the bottom of our constructor self.value equals self.notevaluated. This is where we're going to store the result of calling code with star args and star quargs to memoize the result of our expression. We start it at self.notevaluated so that we know that we don't yet know the value of this thunk. It's still a tree, and we haven't materialized anything. To implement the call for our cell thunk, what we're going to do is first check if self.value is self.notevaluated. This means that we don't yet know the value of this expression, and we need to actually compute it. So what we do is we call self.code, meaning we're going to actually enter the function at this point, and we're going to evaluate all of the positional arguments and evaluate all of the keyword arguments and feed them to this function. We're then going to save the value on self.value. Once we've done that, we can delete self.code, self.args, and self.quargs. This is an important part because if we don't delete the code, the arguments, and the keyword arguments, we're going to always hold on to these values, even though they're not needed anymore. So this is an optimization for reducing the memory usage of this thunk. We don't want to memoize every intermediate expression. We just want to memoize the final result. After that, we're going to return self.value. The way that this implements memoization is that the second time we evaluate this function, we're going to start at the top again, and we'll say, if self.value is self.notevaluated. Since we said before that self.notevaluated is never a valid result of any expression in our system, this branch will immediately return false, in which case we jump right to the return self.value, and we get the result without re-executing our function. So we can rewrite the sub-expression example before. Instead of using a lambda, we will now use a cell thunk. So here we say sub-expression equals cell thunk of f, a, and b. What this is a deferred computation which, when we request its value, will enter the function f passing the arguments a and b. We can then build up a larger expression using this, cell thunk of f and sub-expression and sub-expression. So this is the same expression we had before, which generated that redundant tree. But now, when we request the value of this expression, we see that we print calling f with a equals 1, b equals 2 exactly once. And then we print calling f with a equals 3, b equals 3, because this is the result of our sub-expression, and we get the value 6. Now, some of you might be noticing that f is not actually a pure function. We are printing it only once, so this actually does not perform the same behavior as our original code. We're going to pretend that f was pure, because it's very hard to show you that the function was called only one time if there's no print or side effect that we can observe from outside the function. Another type of deferred computation that we can use is called a self-updating thunk. The way a self-updating thunk works is we start by defining what's called the indirection code. The indirection code is an identity function which takes the value and returns it unchanged. The constructor for our self-updating thunk has the same signature as our self thunk, where we take the function we want to execute and the positional arguments to feed to that function, as well as the keyword arguments to feed. Instead of storing the code directly, what we're going to do is provide a small wrapper for this. What this wrapper does, this wrapper is called update frame, and we're defining it inside our constructor. This function takes positional arguments and keyword arguments, and it feeds them to the original code that we accepted from our constructor. Then we're going to redefine the function that we're storing in this thunk to be that indirection code, or the identity function that we defined earlier. We're then going to redefine the positional arguments to be a tuple containing the single value that we computed before. We're going to set the keyword arguments to empty because we have no new keyword arguments, and then we're going to return the value that we computed from the code that was passed originally. To define the call function for our self-updating thunk, we simply enter the code that we've stored before, evaluating all of the positional arguments and evaluating all of the keyword arguments. The way that this implements memoization is that the first time we enter this function, self.code is set to our update frame. So we will evaluate all of the positional arguments and all of the keyword arguments and go back to our update frame, which will feed those values into the code and produce the value of this expression. Then we set self.code to an identity function. Self.args is going to store the result that we computed, and we have no keyword arguments. The second time we call this dunderCall function to evaluate our expression, self.code will now store the indirection code, or our identity function. We're going to evaluate all of the positional arguments, and that is a tuple that only contains the value we computed. So we will feed the computed value back to an identity function, which will return it unchanged. And we can see that the same example with self thunks, when we use a self-updating thunk, will only evaluate f with a equals 1, b equals 2 exactly once. So this gives us back the graph structure that we were looking for. So as a recap, we have the naive thunks, which are the simple lambda which defers an expression. These thunks are very simple, and they store no state. The cell model thunks are more complex than the naive thunks, but less complex than the self-updating thunks. And this is because they store simple state. They store just the value that was computed or a sentinel value saying that we have not yet computed the function. And then finally, we have the self-updating thunks. These are the most complex of the three thunks I've talked about because it stores the most complex state. In practice, you probably don't want to use the naive thunks because they don't give us the graph-like properties and they don't take advantage of the purity of our functions. And the trade-off between using a cell thunk and a self-updating thunk really comes down to profiling your system and the language that you're implementing this in. So we can talk about more memoization greater than just remembering the result of a single expression. So imagine we rewrote our code from before, but now instead of saving the sub-expression in a single variable, we rewrite the same expression twice. So we have a cell thunk, which represents the function call f of ab, and we have another cell thunk, which represents the same function with the same arguments, though we're storing these in two different deferred computation objects. If we then create a larger expression using both of these, we have f of sub-expression 1 and sub-expression 2. This should be the same as before, because f of a and b is the same in both cases, though when we actually evaluate this function, we see that we go back to calling f with a equals 1, b equals 2 twice, because we evaluate sub-expression 1 and memoize the result on our cell thunk object. Then we call sub-expression 2 and memoize the same result on a different cell thunk object. So this means that we've gone back to a tree which has the redundant left and right subtrees. The way we can get around this is not just by memoizing the result of a single expression, but we can memoize the construction of our deferred objects themselves. So what we start with is a global cache of thunks, and it's empty. And then we accept the code that we want to execute, as well as the positional and keyword arguments. We create a key from the code, the arguments, and the keyword arguments, and we're just using a frozen set there to make the dictionary hashable. We first try to look up the computation that we're about to perform in this global cache. if the computation hasn't been started yet, or no one has ever asked for this expression, we create a new deferred computation, and then we store it in this cache. And then we return this, the value that we've looked up. So if we take our example from before and replace the calls to self-thunk with memoized thunk, we have subexpression 1 as a memoized thunk, subexpression 2 is a memoized thunk. We create our larger expression using both of these deferred computations. And now, when we request the value of result, we go back to calling f of a equals 1, b equals 2 exactly once. And the reason that this works is that subexpression 1 is subexpression 2. So now that these two objects represent the same computation, they're the same object in memory. So we've gone from our tree back to the graph that we wanted in the first place. So now I'd like to walk through a somewhat real example of what this would look like. So we have a function, Fibonacci, and it computes the nth Fibonacci number. So if n is less than or equal to 2, we return 1. Otherwise, we return fib of n minus 1 plus fib of n minus 2. We could walk through what the algorithmic complexity of this function is, but I thought it would be more interesting just to show you what it looked like on my laptop. So fib of 5 runs very quickly, fib of 10 runs less quickly, fib of 15 starting to scale quite poorly, fib of 20 really bad, and then I tried running fib of 100, and it didn't end, so I just killed it and left a dot, dot, dot there. So minutes or hours, I don't really know. So what we have when we call this recursive Fibonacci function that is using eager evaluation is a tree that looks something like this. So we have fib of 5, which internally is the result of fib of 4 plus fib of 3. Fib of 4 is fib of 3 plus fib of 2, and then fib of 3 is fib of 2, fib of 1, and so on. And we can see already that we're going to have a lot of redundant subtrees in order to produce the value that we want. Even just at fib of 5, we can see that we're computing fib of 3 twice. And fib of 2 and fib of 1 are basically identity, but if those were more complicated functions, this would be very slow. If we instead used memoization and lazy evaluation, we could rewrite our Fibonacci function so that instead of returning just fib of n minus 1 plus fib of n minus 2, we would use a memoized thunk to produce the expression which will, when requested, look up the values of this. If we run this on my laptop, we see that fib of 5 is actually much, much slower than the eager fib of 5. And that's because we're doing a lot of overhead to construct all these deferred computations, do all the hash lookups and memoization. And there is some constant overhead to that. But we'll start to see performance wins even at fib of 10 or fib of 15, fib of 20, and I can even run fib of 100. It might look like it ran faster. I think it's just noise on the laptop, but it's not like it gets better as you go. But it means that really the result of doing the computation scales very well now. And that's because if we think about the computation graph required to produce our values, we have fib of 5, which is fib of 4 plus fib of 3, and fib of 4 is fib of 3 plus fib of 2. But now fib of 3 only appears in our graph exactly once. In fact, fib of n will only appear in the graph exactly once. So we've reduced this to a linear problem. So this kind of technique is used in real projects, not just Fibonacci functions. A great project that uses lazy evaluation is Dask, and more specifically, the library dask.delayed. So what dask.delayed does is it uses this deferred computation technique in order to build up a very large graph, which can then be executed in parallel, either using threads, multiple processes, or even against a large compute cluster. Another project that uses this deferred computation idea is Blaze. Blaze defers computation of expressions so that it can perform optimizations or reevaluate that expression against a SQL database, a Mongo database, or NumPy. And then if any of these optimizations look interesting or if this concept was cool for you, I am doing a poster session on optimizing Python programs using lazy evaluation, mostly talking about Dask and some tools that I built. So these slides are available on GitHub. My GitHub name is 10Ls/LazyTalk, and I tweet sometimes. Thank you.
We have about 5 minutes for questions. If you want to come up to the microphones over there and over here.
Out of curiosity, why implement the thunks rather than just use an L or U cache? With the one-line annotation, you could have achieved the same thing.
Yeah, so L or U cache is a way to do the memoization, but what it doesn't allow us to do is build up the graph. And so when you have this large deferred graph, you can do graph operations or graph transformations on the computations. So one thing we didn't really get into was manipulating the thunk objects directly. For example, inspecting what the function is, inspecting what the arguments are, and doing sub-expression elimination at the graph level, or for example, like Dask is using it to execute that graph in parallel. So the LRU cache is a quick way to do the memoization, but not a way to defer all the expressions. Does that make sense?
Yep.
Thank you.
Hi, I really enjoyed this talk. Do you know if there are any problems with Stack Overflow?
Yes, so one thing is that we've introduced a lot of extra frames to perform any computation, though you could get around that with implementing your thunks in a different way. So for example, I have a library called Lazy Python, and it implements cell model thunks, but it's as a C extension, so all of the extra evaluation is happening in C and not in Python.
Hey, you made the theory of this make a lot of sense for me, but I'm still having trouble making the connection to practical applications. You talked about Dask and Blaze. Can you give some more examples of like practical places where lazy evaluation is particularly useful?
Yep. So other projects that are using lazy evaluation heavily are things like Theano or TensorFlow. So the idea is you can define your expression and then evaluate it in different contexts. So once you've built up this large computation graph, it's up to the execution environment to decide how to actually run that code. So by using lazy evaluation, you're like decoupling running your code from the representation of the computation you want to perform.
Yeah, that makes sense. Thank you.
Cool.
I thought this was really cool. Do you think that the memoization of thunk creation would be a good fit for a meta class?
Like for this particular implementation?
Sure.
Yeah, that probably would have been a way to do it. I didn't want to add anything too complicated. I already had a lot of like complicated code on the slides. I'll say in the library I use, I don't actually memoize the thunk creation at creation time. What I do is I take the big computation graph and reduce it at evaluation time. So I'm like lazily memoizing the subtrees, if that makes sense.
Thanks.
So you can go lazy all the way down.
Hi. At the self-changing thunk that you showed, there was a frozen set of the quarks.items.
Yep.
But what if something like a list or a dictionary is in there that's not hashable?
Yeah, so this was just like a very quick cut to just kind of show the idea that don't use that implementation. Yeah. Another problem with that implementation is if you pass an argument positionally or you pass the same argument by keyword, it will generate a different hash key. So it's really not like a robust memoization solution. It was just a way to show the idea quickly.
All right, thanks.
I was just wondering, in kind of debug applications, like how do you debug something like this when now like kind of your tracing is all butchered because you don't know where something actually was computed and like,
yeah.
Things like that.
So that goes back to why eager evaluation is good. I'd say it's really hard to debug your lazy programs because when you actually want to know the value, you have to perform the computation. So stepping through your program in a debugger or some like inspection context, like inspecting a value or scrutinizing the value is going to do the work. So then it's memoized and your program won't behave the same. I don't have any great tips for doing this well other than more like instrumentation of the compute engine itself.
Thanks.
Great talk.
Thank you.
So I see where this fits in as far as simplifying really big, like recursive computations, but how do we bring in the useful world of side effects and be able to do lazy evaluation with side effects and keep track of what happened?
So in Dask.delayed, expressions are not memoized by default. You have to explicitly mark that a function is pure, which means that that subtree will be re-executed every time.
Okay, cool.
Hi. If we're going to introduce like lazy evaluation to say a production web app, what library would you recommend?
So I don't know if I would say to like for web development, I think a better type of model for that would be something like asynchronous programming, where you defer things by sending a work to the event loop, things like async IO. I haven't built any web apps with lazy evaluation, so I don't have any advice for that. Sorry.
Okay, that's it. We don't have any more time, unfortunately. Let's give the speaker a hand again.
Should I just unplug this? There we go. And return that to the caller. So when we write this line, we see that we've immediately printed. So we know that we've already called our function. And when we look at the value of a, we have the integer 3. So we have a concrete value. We can then use this value a in another expression. For example, b equals f of a and 4. We're going to do the same thing when we execute this code, where we load a, which will fetch the value, which is 3. We're then going to load 4, and we're going to enter our function again, generating the format string, calling f with a equals 3 and b equals 4, printing that to the terminal, then adding these numbers and returning it. And when we look at b, we see that it's 7. So we've, again, immediately produced a concrete value, which is the result of this expression. What we're describing here is an evaluation model, which is the way that we execute programs. And in particular, we're describing what's called eager evaluation. Eager evaluation is where you evaluate expressions as they appear in source code. So you go line by line and just start executing code. Expressions immediately produce a concrete value. So when we had the line a equals f of 1, 2, we immediately produced the value 3. And eager evaluation is a choice. So a lot of people, when they learn programming, they learn that computers go line by line and they execute code. But that's not the only way that you could choose to execute code. This is just a choice that has been made for you by the programming language we chose. I will say, though, that
Hello, welcome to the first talk in this session. It's going to be Joe Jevnik, title available on request, Introduction to Lazy Evaluation. Have fun.
Hi, everyone. Thank you for attending. Today, we're going to talk about lazy evaluation. Before we talk about lazy evaluation, I'd like to revisit how we execute programs normally, and more specifically, how we execute Python programs. So if we have some arbitrary function, here we're going to call it f, takes 2 arguments, a and b. This function is going to print the string calling f with a equals and then the value of a, and b equals the value of b. Then this function is going to return the sum of a and b. When we write the line of code a equals f of 1 and 2, what the Python interpreter does is it looks at this line and it says, I need to evaluate the arguments to this function call. So it's going to evaluate the literal 1, which produces the value 1, evaluate the literal 2, which produces the value 2, and then it will immediately enter this function and begin executing lines in the order that they appear in source code. So we're going to hit the first line, which is print and our format string. And what that will do is format the string to produce the actual string we want to print. So we're going to generate calling f with a equals 1 and b equals 2. And then we're going to feed that string to the print function, which will print it to the terminal. Then we're going to hit the line return a plus b, which is going to add a and b together.